I did push it. Okay, yeah. Now it's working.
I think this will be all right.
And the announcement you need to make before we timer is there, you can see it. It will yell that time is up, but
I removed a bunch of slides last night.
all right.
Okay, it would be too long because I tend to over-explain.
I'm sure it will be fine.
Don't need this. But I have some backup slides. Thank you.
You ready? Hi everyone, please take a seat. Welcome back to, what day is today? Fourth day of the Symposium. This is section 3B, the CGM and IGM role in shaping star formation activity in galaxies. So I'm your chair for the morning, Aaron Young. And we're going to kick off the section with a review talk from Freke van der Voet. She will tell us about the role of the circumgalactic and intergalactic medium in galaxy formation. Freke, take it away.
Thank you, thank you. So yes, so I'm Freke van der Voet. I work at Cardiff University, and I'll do my best of giving you an overview of it'll be heavily CGM focused, but I'll also mention the intergalactic medium. And yeah, it's definitely not enough time to tell you everything I would like to, but we'll hopefully give you a nice sort of flavor of why I think, or why I know that the galaxy and the circumgalactic medium are intimately connected. You cannot have one without the other. So I wanted to first, so this is going to be mostly about simulations. I guess I have to click somewhere. And the problem that we have, so I do a lot of cosmological simulations. There's also other methods where you can try to understand the circumgalactic medium better. But one of the main problems that we have as simulators is that the scales relevant in galaxy formation, relevant in star formation, relevant in simulating the whole range of scales important in solving this problem is huge. So this is a cartoon from one of my recent review, and it spans 36 orders of magnitude. So what you want is the full large-scale structure of the universe. Then you get loads of galaxies. You have great statistics, but we can't do that. We are always limited to sort of megaparsec, 100 megaparsec boxes. What you would also like to do is to resolve individual stars, resolve the accretion disks around black holes, and those kinds of things are just completely impossible. And then in order to get down this sort of scale spiral, what's also important very much when you're modeling gas is any sort of gas in interactions of atomic particles because they result in cooling. So all of those things that we can't model directly. So galaxies, we are modeling directly. Some approximations are necessary in the interstellar medium. We're modeling the circumgalactic medium and the intergalactic medium as well, but we cannot do individual stars and all of these things, cooling, star formation, black hole accretion, feedback physics, all of that is included in a very approximate way in what we call subgrid models. So this is now my cartoon of the main processes important in when you want to create a galaxy or provide fuel for star formation. So what you do is from the intergalactic medium, gas flows into the halo, which we now call the circumgalactic medium, and then that flows into your galaxy. Then maybe you have some mergers as well, bringing gas and stars, and if that was the end, then we would be very happy and we could have stopped doing simulations like 20, 30 years ago. However, if you do that, only inflow, only mergers, then you end up with galaxies that are 10 times more massive than they are in the real universe. So, like, you could argue it's a better universe, but it's not the one that we live in. So therefore, we have like decades more work to do in order to like sort of prevent gas from accreting onto galaxies and prevent too many stars from forming. And the way we primarily do this is through large-scale outflows. These can be driven by supernovae or other forms of stellar feedback, and also by supermassive black holes in the centers of these galaxies. This can be done in a variety of different ways. I try to like illustrate that by having some of these outflows, like leaving the halo, going out into the intergalactic medium, maybe never to return. So you need to do a powerful push, and then you don't have to worry about this gas anymore. But some outflows don't reach out that far, so you can do a smaller push, so you need less energy. But then you have the chance that all of this gas, which is now enriched and therefore actually very efficient at cooling, losing its energy, and then falling back onto the galaxy. And then don't forget about mergers. They don't have to merge. They can also just fly by and then lose their gas, and that also is metal rich and therefore wants to accrete onto the galaxy. So, but really our problem is that we need to stop. We need to stop this very efficient process of gas accretion, and that's what we work on. And then I wanted to mention that maybe we also need to worry about magnetic fields, other forms of feedback that are not normally included, etc. This is a figure from Danielle, who will give a talk, I think, tomorrow, just to show you different ways of gas accretion. So in pink, you can see streamlines of gas accreting from the IGM onto the CGM and then later onto the galaxy. So that's called fresh accretion here. There's wind recycling, what I just talked about. So you kick out your gas, but it comes back. And then there's, if you have other galaxies, they can lose their gas, but it then accretes onto the central galaxy. So, and then this is a single galaxy that evolves over time. So you can see that sometimes at some epochs, like for this particular galaxy, mergers are more important, or this intergalactic transfer, sorry. And sometimes this recycling is more important. But confusingly or upsettingly, this is different in like loads of the simulations that we have today. So all of these simulations make like sort of realistic galaxies. So here's Eagle, that's a lower resolution but larger scale simulation, and then Auriga and Fire, they are zoom simulations, so you get better resolution but worse statistics. And in Solid is this IGM accretion, galactic fountains, halo fountains. Recycling is in these dashed curves, and dotted is this transfer from other galaxies. And you can see, if we look at the solid lines, for example, for Fire, this is 20%, for Auriga, it's 10%, and for Eagle, it's 60%. So these simulations that all claim to like do a good job at forming galaxies completely disagree on how they are formed. And this is a nice movie I got from the Illustris TNG website. So the top panels is Illustris, the bottom panels is Illustris TNG. So they start with the same initial conditions, so it's very easy to compare them. Then we have density, temperature, metallicity, and the stellar light. So if you look at the stars, so this is running from redshift 4 to redshift 0, then you can see that they're actually looking fairly similar. But if you start looking at the gas temperature, for example, when AGN feedback kicks in Illustris, it blows like huge, very low density and hot bubbles of, that's just the way this feedback works, and TNG does not do that. It's in a way this calmer form of feedback that I described before. And I just wanted to show you that yes, you make sort of similar galaxies, or similar enough that you wouldn't really be able to say like this galaxy is definitely better than that galaxy, but you're changing the entire, well, in this case, you're changing the CGM as well as the IGM. I think you will all agree that the density of the universe is very different in these two different simulations. And just to like show you sort of like how that then compares to observations and why you maybe could use the CGM, or in this case, it's the intergroup and the intercluster medium in order to constrain galaxy formation models. Here are some observations binned from Giordini et al. Compared to blue is Illustris TNG, and dashed is Illustris. So Illustris blows out all of its gas from the intergroup medium, has only 10% left or so, whereas in TNG it matches those observations much better. So in this case, you could say that I can safely rule out this scenario and safely say that this would be a better representation of our universe. So this is basically making the same point. Like there's loads of simulations now, Eagle, Horizon AGN, TNG, Simba, Firebox. Most of these are publicly available, so you can also use them, as I have used them as well. And they're pretty good at getting reasonable galaxy properties. So they reproduce the galaxy stellar mass function by construction at redshift 0. They reproduce so this is another thing that's often tuned to, which is the galaxy sizes, because it's very easy to create a model where you get the right masses, but you get very, very compact galaxies. So then it's the parameters of the feedback models are tuned such that you get realistic galaxy sizes. That's all done at redshift 0. So the fact that they are still reasonably matching, this is showing it for Eagle and Illustris TNG, for blue and or star-forming and passive galaxies. You can see that at redshift 2 they also match reasonably well. So that's then more of a prediction, because that was not what was tuned to. It was only tuned at redshift 0. So you can still use them. You can't really use them to predict redshift 0, because now you've in terms of galaxy sizes, but you can use it to look at the evolution. However, again, how they do this is very different. So here are some inflow and outflow rates as a function of galactocentric radius. So for halos of 10 to the 11.5, 12, and 12.5 solar masses. And you can see in dashed is Illustris TNG, in solid is Eagle, and I think you'll all agree that in the central 200 kiloparsec or so, the rates, both the inflow and the outflow rates, are much higher in Illustris TNG than they are in Eagle, so they are creating galaxies in a very different way. So, I mean, probably the net growth is actually very similar, otherwise you wouldn't end up with galaxies that are the correct mass, etc. But how they do it is hugely different. And I love this illustration that just appeared on the archive. Oh, it's covered, but it's Wright et al. From Ruby Wright, 2024. And this is showing it for Eagle. How these feedback models effectively work. It's from Eagle on the left, from TNG in the bottom, and Simba on the right. So all of these are these large-scale 100 megaparsec boxes. And it's showing you how stellar feedback works, which is primarily dominant below the Milky Way scale, and then AGN feedback, which primarily dominates at higher masses. So here it's showing you how these different models then behave. So Eagle has the strongest outflows in, so the most powerful outflows for supernova feedback, and then this gas doesn't make it back, but it has the lowest, the least powerful AGN outflows, and again, you can make, there's no way to say like one of them like is the preferred way, but this is just the different ways in how they do this. You do then end up with, of course, a different CGM. You end up, because in one case you're really depleting your CGM you're pushing all your baryons, all your gas out of the CGM into the IGM. And in other cases, you end up with a high baryon fraction. And this is also summarized here. So we have these 3 simulations as well as Romulus, which has a different type of AGN feedback, which is why we added it to this, this figure. And you can see that, so even at the high masses, they are different. Eagle is maybe a little high. This is the CGM mass fraction, or at high masses, you can think of it as the intergroup or intercluster medium. Simba is maybe a little bit low, but they're not hugely different. But well, they are different. I don't know, but it's like I don't know if there's. I think this CGM fraction, especially at high masses, can currently be used to try and constrain these models. But at low masses, they're also behaving super differently. So Eagle just sort of towards low masses decreases and has very low baryon fractions, 10% below the Milky Way mass scale. But something like Illustrious TNG has 50% baryon still included in these low mass halos. So therefore, yeah, they're behaving super differently, but we cannot really tell which one is better. And you can use these simulations then to ask why is it this level, and what sets the scatter. So here's showing you the full data, so you can see that at low masses, it's actually not a tight relation. There's a huge scatter going all the way from like 100% of the baryon fraction to almost none. And this scales with how massive the black hole is, which is a proxy for how much feedback this black hole has done. Because the more massive your black hole, the more energy was available for feedback. So you end up blowing out your baryons much more when you do that. It then also scales with the star formation rate, because if you've done a lot of feedback, you now have also not just depleted your baryons from the CGM, but also from the IGM. So it also correlates with the star formation rate. And therefore, it's important to sort of ask, like, what is the most important, like, what does it correlate with most strongly? Because all of these things are intimately connected. So this is work by Mate et al. In 2019 using Eagle. So this is the specific star formation rate versus the stellar mass. And then color-coded by the formation time of the halo. So it's the redshift at which half of the dark matter was assembled. So it's sort of the half mass time. And you can see that there's a strong correlation. So the galaxies that are forming stars, at the slowest, or the lowest star formation rates, preferentially formed early, and the stars and the galaxies that are forming stars very efficiently primarily formed late, even though they have the same mass at the current time. So this is then interpreted as saying, okay, so the reason the halo formation time correlates is because if you form early, you do early feedback when your universe is still nice and tiny, so it's easier to blow out your gas. You deplete your CGM from baryons, and you have an easier time removing the gas and preventing star formation, or preventing gas from accreting and thus preventing star formation. So these are some also very recent plots that I want to walk you through, because this is, so there's something you can do with Zoom simulations, or basically any simulations, that is like a very powerful experiment, because if you change the initial conditions such that, like, just by a tiny amount, you can change the timing of a merger, or you can change, so it's still the same halo with the same environment, the same sort of accretion history, except you're changing one specific small aspect of of the halo assembly. And that's what these authors did. So here you can see how this galaxy grows over time. So there's 2 different variations. So in one case, they made the halo and the galaxy therefore assemble earlier. So everything else is the same, but it starts earlier or later. And in the other case, they increase the importance of a merger. So the 2 blue ones don't have any mergers that are more than 1 to 10. And then the 2 orange-ready ones are ones where it goes up to a merger of 1 to 2, I think, or almost 1 to 2. And then one of them, so the dark red one is forming early, the orange one is forming late, the dark blue one is forming early, and the lighter blue one is forming late. So what you can see, if you look only at the blue curve, so the dark blue one forms earlier, they reach basically the same stellar mass in total, but if you look at the star formation rate, like they're all the same, even though one of them formed earlier and one of them formed later. And I just told you that there's a strong correlation with halos that form earlier have lower star formation rates, and galaxies that form later later have higher star formation rates. And that is not what you see when you look at the exact same halo, except the only change being when it forms. So there has to be something else that's happening. Well, you've already seen the merger reason now, but mergers. If you look at the two red ones, they also end up forming basically the same amount of stellar mass. But if you look at the specific star formation rates, you can see that when these merger happens, which is indicated by the vertical lines, then the star formation actually drops, and these galaxies then spend a lot of time in the green valley, or maybe even, and some of them, so there's like 10 realizations for each one, some of them actually go below the green valley. And the reason that this happens is related to AGN feedback again. So again, this is specific for this model, which is based on Eagle. We should be careful that we also check this in using other prescriptions. But what happens in this simulation is that because of the merger, the black hole, so the black hole mass is here, the energy output is on the left axis. Because the merger happens, the gas disk gets destroyed, and it's much easier for the gas to accrete onto the central black hole, and the black hole grows more and therefore does more feedback. And what happens in the secular ones that don't have a merger, they just have a nice disk set up, and it's very hard for the gas to get to the center of this galaxy. And it just sort of, the gas disk and the black hole sort of get decoupled. Like the gas disk is doing what it wants, it's forming stars, and the black hole is locally evacuating a small part and therefore not accreting, and therefore you don't get this very efficient AGN feedback that you do get here. And then here's the resulting baryon fraction in the CGM. So you can see that you then get this huge scatter. So if this is the correct picture, then it's not actually either the binding energy or the halo formation time that is setting these differences, but like how many mergers or how the mergers have really messed up the morphology of the gas disk of the galaxies. Okay, so I hope I hope I did a good job explaining that. It's quite an interesting paper. I can recommend reading it. But I wanted to mention something about the intergalactic medium and whether or not that is important when you want to understand like how the galaxies are fed. And so this is work by Martizzi et al. In 2 papers. So what they did is you have your dark matter density fields. You can then smooth it over some like 4 megaparsecs or something in order to get an idea of where the overdensities and underdensities are. And you can also use some specific classification to say, okay, is it in a void? Is it in a filament? Is it living in a knot of the cosmic web? And so they did this, and then so there's a lot of statistical tests you can do. I picked one. So, pardon me. Where they calculate like how much of the variance in stellar mass at fixed stellar mass, so how much of the scatter is set by these 3 different things. So, by the overdensity, like this one, by the cosmic web class, and by the formation time of the halo, and then black is like all of them together. So I think you'll agree that like it seems to be mostly driven by the sort of smaller scale, large scale structure, rather than by the super large scale overdensities that are happening on 5 megaparsec or so, or cosmic web class. Doesn't mean it doesn't do anything, especially at redshift 0, it does become a little bit more important. But overall, I think that these sort of large scale effects are not dominant. But I did want to just have a very quick point that, of course, it matters very much if you're a satellite living in a halo that is much more massive than you are. So here, this is what a central galaxy would look like in density and temperature. This is Eagle. If it's living in a host galaxy, this galaxy 10 to the 10 solar masses in stellar mass. If it's living in a halo that's like a little bit more massive than its own its own sort of central halo would be, you can see that there's differences. It's definitely truncated, but it still has high density material around it and is probably still able to accrete. Whereas if the same galaxy, so this is the gas density, so you can't see the stars, but they're indicated by this circle, the half mass radius. If it's living in a group, for example, this galaxy would most likely have most of its gas stripped away, and therefore it has a hard time accreting. And here that's quantified. So the central galaxies are accreting mostly at this rate, whereas if you're a satellite living in a cluster, you're mostly not accreting at all, only if the difference between you and your host is different. And this is probably just due to the ram pressure being much stronger in more massive halos. So the CGM structure is complex. So all of this didn't really so this is where a lot of like CGM research is focusing on right now. So this is from a review by Fauché-Giguère and O, and it's a cartoon, but it's showing you so all of the things I showed you before, like inflows, outflows, but it's making the point that all of this has huge structure. I think everybody here will probably know this, but like even this small scale structure, if you zoom in, like it's not a single cloud. It has parsec scale clumps, and then if you zoom into that, then you see like even the interfaces between the cold gas or cool 10 to the 4 and the hot gas 10 to the 6-ish, like is super complex and not like a nice discontinuity. So we try to incorporate this in our simulations, but even with these idealized simulations, so this is a cold blob living in a wind tunnel at sub-parsec resolution. Even there you can see as you go to higher resolution, this cloud gets destroyed by the oncoming wind, but it gets like destroyed into more pieces. And if you look at the front of this cloud, you're also seeing that actually the acceleration is different. So there's like no hope that we could, like, well, this is not converged, and this is like many, many orders of magnitude better than any simulation that I've ever done. And even that one is not converged. So we have a huge problem, but that doesn't stop us from trying to work on it. So this is something from my work, which is increasing the resolution locally by a factor of 100 in the CGM. And I just wanted to make the point that like it can look very different. So if you were to observe this halo in H1, you would find a lot more cool gas if you had this halo versus that one. So you might think that this cool gas will then really change the accretion onto the galaxy and thus the subsequent star formation. But the galaxy is actually the same mass as it in both simulations, has similar bulge to total ratio, has a similar star formation history. So just because something changes about your CGM, and of course you need to be careful when you compare it to observations that you know what's going on. If it's not converged, it's important that you know that, but it doesn't mean it necessarily immediately affects your galaxy. Magnetic field is also important. Maybe, I guess we're arguing about that. With a habitable worlds observatory, as Sanj said, we can like just do so many more sightlines and get so much more information about like multiple sightlines through the same halo, but you can also slice and dice it in order to make like azimuthal samples where some are probing the outflows, inflows, etc. But I think what's also very cool is that we will be able to make emission maps, and in combination with other existing or upcoming things, observatories doing X-rays, doing 21 centimeter, doing optical, I think we can really build like a full picture of the CGM, and then I'll stop there. Thank you.
Okay, I think we have time for one or two short questions.
So my question is that I'm asking from the point of view of an observer. We measure column densities, but they're not sometimes perfect, but we also have the access to measure kinematics. And I was just wondering if there are, like, what is your basically opinion, or your based on your understanding of these simulations, if kinematically we can distinguish between some of these models versus just the content?
I mean, I think it would be worth to try. It would be worth it to try. I don't know, but it's possible that you would see different kinematics in when your feedback model is working very differently, and that I think is much more resolution independent. So I think that could be very powerful. Yeah.
Let's take one more question. Imad, you can come set up. I saw a hand in the back before, right? Any other questions? Right here.
So what about magnetic fields?
Well, okay, so there are other groups that say they don't make any difference, but in my simulations, the galaxy changes sizes, so you get more extended disks with magnetic fields, and it changes the outflow. It makes them more collimated and more slow than in the case without magnetic fields. Which then, this is the metallicity distribution. So then it changes like all your properties in the CGM as well when you change sort of the outflow speed and the sort of the outflow opening cone. But this is very Milky Way centric, so it just doesn't necessarily apply to like all halo masses. Thank you.
Great. Thanks, Freki, again. Okay, next we're going to hear from Imad Pasha. He's going to tell us about bridging observations and simulations of the resolved CGM. Take it away.
Great, thanks. Yeah, my name is Imad Pasha. I'm a sixth-year grad student at Yale University. And today I'm going to be doing, I think, maybe the first instrumentation talk of this conference. And so what I'm going to be talking about is this instrument here, the Dragonfly Spectral Line Mapper. This is actually just 1/4 of it. And I've listed some of my collaborators and other students who are working on this project over there on the right. So I think the really exciting thing to start with, we just saw this really nice figure, is that the spatially resolved CGM around individual galaxies is actually nearly within our grasp. And with instruments like Keck, KCWI, and KCRM, VLT Muse, as well as upcoming spectrographs like CHAS, and as I'll explain with Dragonfly, we really have the opportunity to go and map where the gas is in the CGM in emission. And I think we can all agree that this is really something we need to do. Because if a decade of absorption line studies and simulations have told us anything, it's that the CGM around individual galaxies is a complex and dynamic environment, and one sight line is not really enough to characterize this whole picture. But if we want to understand how the star formation in the galaxies that sit in the center of these dramatically different halos, despite having the same star formation rates and stellar masses, actually is regulated, then we really need to understand how the CGM is processing the gas that's inflowing and outflowing from these galaxies. Now, coming back to the idea of KCWI, I love KCWI, I use it, it's an amazing instrument. If you wanted to study the CGM around a nearby edge-on spiral galaxy, you would find that the number of pointings you would need would be a little bit daunting. And so, my argument is that we do want to look at these types of galaxies because we can actually measure their ISM properties at extremely high resolution. And if we want to start putting together this picture of how the CGM and IGM, or CGM and ISM actually couple to one another, then these are great examples to look at. And so that's why the Dragonfly Spectral Line Mapper, I'll argue, is the perfect instrument to complement Keck and Muse here in the local universe. So this outer blue box is our field of view of 1.5 by 1.9 degrees. And you can see that this is really well tuned to actually contain the entire virial radius of these nearby galaxies in nearly a single pointing, and importantly on a single chip, so no mosaicing of your detectors, which really helps when you're trying to go after really large scale, really low surface brightness emission. And to that note, we obviously need more than a large field of view to see the CGM. We all know that the gas is extremely diffuse and faint. And so that is where the other sort of technological piece comes in, and that is using Canon telephoto lenses strapped together to do astronomy. So some of you may be familiar with this. This is the original Dragonfly telescope, one of two mounts that Bob Abraham and Peter Van Dokkum, my advisor, came up with back in 2014. And it turns out that refracting telescopes like this are extremely good for low surface brightness astronomy because they minimize internal reflections, both from not having a big mirror and open design, but also from Canon spending millions of dollars in R&D on nano coatings on the optical elements. They're also optically fast systems. You get this sort of built-in dithering and redundancy in a very large field of view. And so, the original Dragonfly has done really interesting work in the field of stellar sort of light, so G and R bands discovering things like ultra-diffuse galaxies. And now what we've done is put ultra-narrowband filters in front of this type of optical setup in order to go after the gas. Now, this is actually helpful in two ways. By moving filters out here in front of the lenses instead of in the converging beam inside where your instrument would normally be, we can make our filters narrower than a conventional narrowband filter. And that actually allows us to tilt our filters to access different spectral lines like H alpha and N2 cleanly and separably in the same galaxy. Or we can go after one line like H alpha and tilt in order to get different velocity ranges. So our full velocity width is about 480, 490 kilometers a second. But with some careful tilting, we can actually get better resolution than that and actually see things perhaps like bulk rotation of the CGM and whether it matches galaxies. You get a third benefit other than increased signal to noise when you have very narrow filters. This gray region here shows the way the region of H alpha in the local universe at different velocities. And you can see there are some skylines that would sort of contaminate your signal or make it really hard to get down to really, really narrow or really, really deep images. Our new filters, these sort of green ones, are able to actually slip between those skylines. And so we get the additional benefit there. So this is Deb Lockhorst, now at NRC, constructing what was a 3-lens Pathfinder array, which had 3 nanometer filters instead of our current 0.8 nanometers. We're being a little bit casual with those very expensive lenses down there. What we were able to do with this instrument was go after M82, our friendly neighbor, and most famous starburst ever. This is, I should have a citation, this is Devine, 1999, I believe, a very famous image of M82 that was one of the discovery images for this H alpha cap 11 kiloparsecs above the disk. You can also see this huge optical artifact in the image. That's one of the struggles when you're trying to do low surface brightness astronomy with a mirror-based telescope design. Here is the Dragonfly image overlaid. So you can see we detect this diffuse component of H alpha to very large radii off of the disk. We get the cap very easily, and also some new structures that hadn't been seen before. And speaking of new structures, if we zoom way out to our only a fraction of our field of view, actually, there's this huge shell-like feature out at nearly the radius of M82. Now, this is real. We went after it with Keck and got a spectrum. And I'm not going to talk too much about this, but I recommend checking out Deb's paper from 2022. We also have other papers out about what we discovered in the M82 group. And so, it's really just highlighting the types of things we're going to start to hopefully see with this instrument. So the last point that I want to re-emphasize again is the value of being able to separate N2, H alpha, and then also have O3. We'll sort of be able to construct these spatially resolved BPT sort of ratios out in the CGM. And so by having essentially N2 over H alpha or O3 over H alpha, we don't have H beta filters, we'll be able to start tracking the actual sources of ionization for this gas, whether it's photoionization or collisional shocks, et cetera. So what have we been doing since M82? Mostly a massive upgrade of the instrument from 3 lenses up to 120 total lenses split across these 4 mounts. It's actually technically 110 lenses. We're waiting on a couple at the end. And so, we're bringing these 4 mounts online to really now scale that whole thing up and go after some of this faint emission in the CGM. And we now have our sort of full complement of filters. So we have H alpha or N2, depending on how you tilt, O3, our off-bands, continuum filters for both O3 and H alpha, and even skyline monitoring filters to track what the skylines are doing in the vicinity of H alpha. So I'm going to tease a little bit of data. This is NGC 3079, which is a nearby galaxy starbursting, has some outflows that have been seen in the X-ray and FUV. And the deepest data of this galaxy that I could find deals with a lot of the sort of same artifacts and things that we're used to seeing. And this is their sort of high contrast, highly scaled image that tries to get at the faint emission in H alpha. And this is 2.5 hours with DSLM effective. So, putting these two side by side, we can see, again, like in M82, we don't resolve some of these individual little cloudlets, but we are starting to pick up this more diffuse extended component. I'll indicate that this could not be more preliminary, but I would stay tuned for what I think will be some exciting new images coming out very soon with this instrument. I think we have a couple of mounts that are observing and a couple that are being problem children. I just want to kind of end by pointing out that we're building this instrument to go after the faintest kind of emission that's been seen. But the optical setup is great for resolving the disk of nearby galaxies. And if this is something that's of interest to some people, we can actually create very homogeneous, very well characterized maps in these emission lines. We can go even closer. This is not quite HST resolution, but with our field of view, we can get sort of beautiful images of things like nebulae. And if we're interested in star formation regulation and leakage out of H2 regions and things like that, there may be some interesting science that Dragonfly will be able to help with as well. So I'll end with the question, which is just, how do we bridge upcoming observations and simulations? I'll kind of skip through a lot because Freka covered a lot of this, but the point is that there's been a lot of really interesting work that's being done for how we actually simulate the CGM, what we're trying to do. Some or all of these effects may be important, and I think the takeaway point that I want to really make is that we're now poised to answer these key questions about the circumgalactic medium, but we need predicted emission from simulations now. Like, this is the time to do this. And so I'll sort of leave, so just to say, there's some work that we're doing in our group, working with others, trying to make these sort of maps. So this is H alpha using the Colt radiative transfer code on the Fire galaxies. And I'm also working on some TNG50 maps, but there are so many great simulations out there, some of which focus really intensely on the circumgalactic medium. And so we would love to make maps, to work with everybody, to put together the types of things where we can actually predict, make actual quantitative predictions. And so I'll finish with these takeoff slides. If you're an observer, please talk to us about targets. If you're a simulator, please talk to us about predictions. And I have a couple other projects if you want to come talk to me about them later. Thanks.
Let's talk. Okay, questions? There's one in the back first.
So for the filter tilting technique that you used, is there a limit for how far you can go?
Yes. So we can tilt our filters to around 20 degrees or so. And that's a limitation not just of how much we can physically tilt, but also as you tilt the interference filters particularly far, you start losing the sort of monochromatic patch down to below about a degree, which is our field of view. So yeah, typically we're currently tilting between 0 and 20 degrees, and that corresponds to a velocity range out to around 4,000 kilometers a second. And so, in theory, we could make filters that started at a different wavelength and went out farther, but this is just the initial set that we've started with.
Thank you, brilliant talk. I was just wondering, is there any plans in the pipeline of looking at filters that could potentially be used to capture line emission from higher redshift galaxies where you see these emission lines redshifted?
Yeah, that's a great question. So that's definitely something we've been thinking about. Like question 0 on that line is, at what redshifts do certain lines of interest move into the band passes we already have? And so we were looking at that a little bit. MG2 and Lyman alpha will, at some redshift, move into some of our band passes. And so that's step number 1. But yeah, the really great thing about having a modular design where every lens can have its own filter is we can choose, if we do an observing campaign for the next year using these filters, we can decide now we want to go after a different line or a different redshift, and we can just replace the filters on 1, 2, 3 of the mounts and go after it there. So yeah, definitely something that's like kicking around. We're thinking about what might be the next best steps after.
Exciting. Thank you very much.
Daniela?
Thank you very much. Okay, so this is a little bit of a half-baked question. And there have been many images showing that, for instance, dust survives being ejected in outflows, and it might actually get distributed and survive to larger scales. And I don't know how realistic it might be to actually be able to put an H-beta filter, because creating, for instance, BPT diagram, I doubt it will have much of an impact, even if there is a little bit of dust. But it would be nice to really finally quantify how much dust there is out there.
Absolutely, yeah. So, right, our current filter set sort of makes the implicit assumption that we're not going to have a ton of dust out far into the CGM. But we don't know for sure, and so yeah, an H-beta filter is absolutely something we could do. There's nothing technically stopping us from doing that, and so yeah, I would guess that as this observing campaign goes on and we consider what filters we might want to get, we might go after an H-beta filter. It is unfortunate that for H-alpha and N2 it's so beautiful we can just tilt the same filter, and we can't do the same for O3 and H-beta, but yeah, that's definitely something to consider.
One last question. Go ahead. Oh, sorry. Who's first? Go ahead, I guess.
Question, like what's the spatial resolution?
Yeah, so this is actually changing a little bit. The images that I showed today were binned 2x2 on detector for a spatial resolution of around like 4 and a bit arc seconds. We're actually upgrading all of the cameras to new CMOS detectors, and the final resolution that we'll have there, I think, is closer to like 2 arc seconds. So that's kind of about the scale we're on.
In the interest of time, let's move on. Let's thank Imad again. Next speaker is Vidai. Oh, sorry, Dabi. All right.
Hello, hello. Okay. Which button? This button. Yeah. This button. This. Yeah. This one. That's a laser pointer. Yes. Okay. Okay.
So
thank you.
Next up, Dabi will tell us about circumgalactic medium at high redshift, connecting cosmological filaments with central galaxies. Dabi, take it away.
Yeah. Thank you. My name is Dabi, and I come from University of Concepcion in Chile. Now I'm a postdoctor. And today I'm going to talk about the CGM in high redshift because I'm doing numerical simulations. So for this work, I would like to thanks to my collaborator Isaac Schlossman and Emilio Ramirez Diaz, and also thanks for the supporting from Carter Center in Chile and the University of Kentucky. So why we want to investigate? Because in the past decades, the numerical simulation has already successfully shown how the dark matter forms this cosmic web. For example, this is all dark matter particles. You can form the halos, the filaments, and the wall, and the other large structures. And if you zoom in, you can also see the gas follow this potential wave generated by dark matter, and it collapses in the center, and finally you can form galaxy in the center. But the details how the gas following this larger structure like filaments into the center galaxy is still unknown. So we want to use a numerical simulation to take a look. So our simulation uses a gizmo code, which is n-body hydrodynamic code, and we use the cosmology parameter come from Planck 2060. To save time, we run zooming cosmology simulation, which means first we run a low resolution dark matter only simulations in a larger volume, and then we can just pick up which halo we are interested in and just zoom in this halo in a small volume. And because we know the environment will play a very important in the galaxy evolution, and even for the same halos, when it's at a different cosmic time, the accretion history and tidal events may be very different. So we play the identical halo mass at a different redshift for comparison, saying we have a redshift 6, 4, and 2. And the resolution in our simulation is around 10 parsec at redshift 6, 15 at redshift 4, and 25 at redshift 2. And also we use the Spring-Hunquist 2002 two-phase mode for the stellar star formation recipes, and which include supernova 2 feedback, and also we including the galactic wind feedback. For comparison, we include we apply two different wind feedback for comparison. First one is a constant wind, which means your wind velocity is a constant. We use something like 484 kilometers per second. And another is a variable wind, as it says, it's the velocity wind can be variable proportional to the escape velocity for the halos. We have calculated the total kinematic energy of these two wind feedback. Actually, you can see the variable wind has something like 8 times stronger than the constant wind. So here I summarize our numerical sets. So we have a Milky Way type dark matter halos, which give you around 7 times 10 to the 11 solar mass. And we divide all our halos into catalog. One is the halos in average density, it means average background density, and we have also the overdensity environment. And we play it in 3 different redshift 6, 4, and 2. And also for each halo, we apply 2 different wind feedback for comparison. So totally, we have 12 halos. So with all this setting, after we finish these simulations, we get the final productions, and we want to identify the baryonic filaments. We use the method called D-wave. This is a method just widely used on dark matter, but we apply to the baryons. So the main idea of this method, you can calculate depends on the potential field, depends on the potential field. You can calculate the tidal matrix of it, and then you can calculate the eigenvalue of this matrix, and it depends on the positive or negative of these eigenvalues. You can separate the whole volume into different elements, something like the void, which is green, and the walls, which is green, and also you have the filament, which is red, and the nodes is blue. But considering we are interested in the gas, so and we also know the gas tend to have a low entropy inside the filaments. So we add an extra criterion. This is entropy cutoff. So after we separate these different elements and we found the filaments, we just pick up one. Here is show example come from one filament. The dashed line here represents the Weyl radius, which is around 200 kiloparsec. And this is the same filament come from redshift 2 galaxy, redshift 2 halo, and it's colored with density, temperature, metallicity, and inflow radial velocity. And you can see clearly here you have a very obvious spinal structure in the center. And if you look at the temperature, you can see when the gas following this filament into the center is heated up dramatically near the galaxies. To look at this more carefully, we also plot a cross-section projection at each radius from left to right. We have the radius outside the Weyl radius around 350 kiloparsec and close to a galaxy around 50 kiloparsec. And from these figures, you can see by the way, it's colored with the density. So from here, you can see at the outside, you have a quite high density core structure in the center. Then when it goes in, it's split into several, something like spaghetti flows. And finally, when you close to your galaxies, this structure seems like not so obviously. So we also check the velocity field. Here it shows the same filaments both on face-on direction and edge-on direction, and we have two scales. The top panel shows a halo scale, which the dashed line still represent the Weyl radius. And if you zoom in, you have the galaxy scales, and it's colored with temperature, and this velocity direction shows as these arrows. So you can see when the gas flows from outside the Weyl radius to the center galaxy, you can see how the velocity field changes. It's become more chaotic near the galaxies. If you look at this scale, it's around 30 kiloparsec for our galaxy. And also, if you look at the edge-on from here, you can see how some of because the filament is much thinner than your galaxy scale, so some of the filaments just miss the center galaxy, and then they just return to the CGM. Also, we want to check the turbulence level for the galaxy, and here is a very similar figure like the previous one, but we colored it with the vorticity, which is defined as the curve of the velocity field. And from here, you can see this inside the filament, you have a very high vorticity structure, which is exactly alongside the core structure which we already see in previous. So we consider this is maybe triggered with Kerr-Helmholtz instability. And also, if you look at the galaxy scale, you can see how dramatically the vorticity increase near the galaxies. So this can be also triggered by the ablation of the stream gas, which we show it when you close to a galaxy, so you don't see this spaghetti structure so clearly. So here is the accretion and accretion and outflow rates as a function of the radius for all our galaxies. We have redshift 6, 4, and 2, and the solid line represents accretion and dashed line represents outflows, and different color represent different wind feedback. For the CW, for the constant wind feedback is blue, and the variable feedback is red. And from here, if you compare different redshift, you can see the accretion rate seems like decreasing with decreasing redshift. And also, we found it seems like all our galaxies outflow only extend to around 150 kiloparsec. So finally, we want to have a big picture of our our CGM, which means inside the Weyl radius volume. So we calculate the hot to cold gas ratio as a function of radius, and we found there is a dramatically drop around 0.5 Weyl radius. So we divide the whole volume inside Weyl radius into regions. We call the volume inside 0.5 Weyl radius inner CGM, and outside it we call the out CGMs, and we plot the evolution as a mass evolution of mass, temperature, and metallicity as a function of redshift. And you can see there is a separation between the temperature and metallicity of inner and outer regions, and you can see the the inner part you have a higher metallicity. So we think the inner CGM is more dominated by the galactic feedback. So here is a summarize. We have our simulations show the filament has core structures, and it will dissolve into spaghetti type flows. And also our turbulence increased dramatically inside something like 30 kilopascal around your galaxies, and it may be triggered with the ablation of the streamers. And our CGM is multi-phase, not a thermodynamic or dynamic equilibrium. And finally, our galactic outflows affects mostly about 0.5 radius. That's all. Thank you.
Thank you, Da, for the nice talk. Let's take some questions. Questions from the room. Okay, all right, go ahead.
Could these cosmological streams imprint rotation in the massive galaxy that will be formed at the very center of this massive dark matter halos?
Sorry, I don't quite get your question.
Well, the stream that implies a very massive input of gas, could it imprint rotation in the proto-galaxy being formed at high redshifts?
Yeah, actually,
in these massive halos.
Yeah, actually, we create some movies for this simulation, and we can see it sometimes that this. As you said, we have several filaments. Not all. This is only one example. We have several filaments. They come from different directions. Sometimes this galaxy rotate proportional to this inflow velocity. But actually, in high redshift, you have really frequency tidal events. It means something like the galaxy merger or minor merger. This can completely destroy your disk. So sometimes you can get something like the opposite direction of this rotation comparing to your inflow filaments. So we do not have something like a quantity, something like a measurement for this, but I don't think the inflow directions will finally determine the galaxy rotation directions. But this can be some factor, but it's not it's the only decisive, something like a key factor for that. Actually, I remember in literally other simulations have something like test for this, and they also find something like the counterclock, something like rotation directions. It's not the same direction like how your filament fitting inside your galaxy. And also sometimes for these filaments is something like your filaments just falling in with a not so large angle of this large angle with respect to the disk plane. But in some case, you can also have something like where something like a 90-degree inflow from these filaments.
Okay, thank you.
Thanks. Any other question? One in the middle.
Thanks. So very interesting talk. I just wonder, so you mentioned about outflows, and I imagine that's gonna be related to both the feedback recipe, and also I wonder how you can distinguish between feedback introduced outflow and actually the tidal being thrown out from your inflow.
Yeah, that's a very good question. Actually, I try to avoid to talk about this. So yes, that's a very good question, because in simulations, feedbacks you can have different recipes for feedback, and actually you do not have a very strict to say this feedback is really something like so realistic. And in our case, first I should say in our simulations we do not have agent feedback at all. So this is, but we still want to some kind of a calibrate how the feedback affects on these things. So that's why we apply two different stellar feedback. And as I said, the variable feedback is something like generally something like 8 times stronger than the constant feedback. And you can see the extended radius is more or less the same. So I don't think this scale is something like really depends on the intensity of this feedback. But also I need to. I cannot 100% to guarantee this because although we have two different stellar wind feedback, but they are all, the implement of this feedback is all called wind particles, which means when you have a star forming region, you kick up some surrounding particles, you just decouple them with hydrodynamic fixed temperature and give an additional wind velocity to kick them out. And when you reach some criterion, you just couple it with hydrodynamic again. So this is only one implement of the wind feedback. And some other simulation may have different implement that may change the scale, scaling. So that's I cannot guarantee for that. But actually, you can. This is something like a difficulty because we do not actually know the undergoing physical mechanical of the galactic wind feedback, so you cannot actually do it in something like from the first principle to do this feedback. Yeah.
Thank you. In the interest of time, let's move on.
Thank you. Oh, sorry. Sorry.
This is the mic. I can change slides.
Yeah, okay.
I did the mic. Okay. Put this on. Last but not least,
Hello.
we're going to hear from Chris. Chris is going to tell us about regulating star formation with a hot circumgalactic medium. Take it away.
Thank you, Aaron. Hello, I'm Chris Carr, and I'm a graduate student at Columbia, and I'm excited to talk to you about some recent work done in collaboration with these wonderful people that will hopefully contribute to this discussion about how star formation can be regulated on all scales, including the circumgalactic scale. And so supernova feedback is believed to be a powerful regulator of star formation in low-mass galaxies, not only on the ISM scale, as we learned on day one, but also on the galactic scale. So in the simple picture, you have these hot overlapping bubbles that expand around the supernova that break out from the galaxy while also entraining cool gas from the interstellar medium, which go on to create these large-scale, multi-phase winds shown here quite spectacularly in the M82 outflow that go on to carry mass, energy, and metals out of the galaxy and into the CGM and possibly even the IGM. And we can quantify how effective these outflows are at transferring mass out of the galaxy by defining a very familiar term here, which is the mass loading factor, which is simply a ratio of the outflowing gas in the wind divided by the star formation rate. And from some of the earliest simulaic models of galaxy formation to the current cutting-edge subgrid implementations of many modern cosmological simulations, eta M here is typically quite large, much, much greater than 1, especially in these low mass systems, in order to reproduce not only the low gas fractions in these systems, but also the low metallicity fractions and the low star formation rates. However, when we actually try to measure the properties of these galactic winds in the real universe, the picture seems a lot less clear. And so this is a collection of a few attempts to actually measure mass loading factors out in the real universe. These are a collection of studies primarily using deep H alpha observations and to some UV pencil beam observations, primarily the warm phase of the outflow. compared to a few predictions from a few different cosmological simulations. And so I really want to point out two important things on this plot. They call it beta, it's actually eta m. First of all is that different cosmological simulations can give very different predictions for what the mass loading should be. Like for example, as we learned earlier, mass outflows can be quite large in TNG 50 compared to Eagle, for example. The other important thing to point out is that observations, even those probing galaxies of similar stellar masses, and even probing similar phases, can give drastically different predictions for what the mass loading ought to be. And of course, we learned earlier that there are many different problems that come with doing these sorts of comparisons between simulations and measured outflows in the real universe. There's been lots of talk of fruit at this conference and the horrible things that happen when you compare different fruits. But I kind of want to ask a different question, I think a more interesting and provocative question, which is, if we're trying to understand how these galactic winds regulate star formation in these low mass systems, is mass loading really the most important thing we should be thinking about and how this process works? Because remember that these winds are multi-phase. And then not only are there cooler phases which carry mass, but as we learned yesterday from Sebastian Lopez's talk, that there are other phases of these winds, particularly hot, diffuse phases, which may not carry that much mass, but they do carry energy. And this is also reflected in more in resolved ISM patch scale simulations, which actually try to generate these galactic winds self-consistently. And what they find is that the majority of the mass is carried in these cooler phases, but the majority of the energy is captured in this diffuse, fast-moving hot phase. And you can measure the fraction of how much energy is escaping in these winds that were released in the supernova by defining another term, which is the energy loading factor. And here is a sort of a collection of different measurements of energy loading across these sort of different small-scale box simulations. And they typically find values of eta E of around the order of 10, maybe 20%. But you can actually get eta E values even greater depending on how clustered your supernova are, not only in time, but in space, and also the environments that these supernovae find themselves embedded in when they go off. And so what we're really going to explore here is what does this energy loading do for us in these winds, and how does it sort of shape this picture of thinking about how galaxies, particularly low-mass galaxies, regulate their star formation. And so to get about this, to understand flows in galaxies, many folks in the past have used these very simple toy regulator models where you can treat each of the different components of the galaxy, both the ISM, the stars, the CGM, as these reservoirs or bathtubs, as sometimes they're called. And you can track the flows between these different reservoirs as sink and source terms in a system of coupled first-order ordinary differential equations. And you can solve, and so given some initial condition, you can solve this system of ordinary differential equations to get solutions for the mass and metal content of each of these different reservoirs as a function of time. And the mass loading here is just a free parameter that you're sort of free to adjust to see how that affects, it's a free variable that you can adjust to see how it affects the properties of your state variables, such as the stellar mass, the gas mass, CGM mass, and so forth. But the real innovation of our approach is that we're not only tracking the flows of mass and metals between the different reservoirs, but the flows in energy as well. And so through this accounting of the global thermal energetics of the CGM, it allows for an extremely simplified but self-consistent treatment of the heating and cooling of the CGM within the regulator model framework. And also point to a few companion papers which have also tried expanding on this model, one led by Viraj Pandya, which you'll hear about more later today. And so to get more into the details of how tracking the energy could affect this sort of global picture of star formation, so first, you have the winds themselves. So you have the stars that go off, some fraction of them detonate as supernova, and they inject these hot winds which deliver energy to the CGM, and that rate is proportional to your energy loading factor. And so this gives the gas of the CGM additional thermal pressure support against gravity. And so when that thermal pressure support is able to exceed that restoring force of gravity, this can overpressurize this CGM and lead to this large-scale expansion of the surrounding gas. And we approximate this using some analytical form here, and we assume that this expansion of the CGM beyond the virial radius, and beyond the bounds of the dark matter halo, occurs on the order of the sound speed of the system. And so in this thermal expansion, not only are you venting out energy, but you're also taking with it a considerable amount of mass with it as well, and you can estimate that just by considering the specific energy of the CGM. And so in this large-scale expansion of the galactic atmosphere, not only are you raising the temperature, but you've also lowered the density, which affects the cooling efficiency of the CGM gas. And so this affects how much gas is actually able to accrete to the ISM and acting as a regulator of the resulting star formation in your system. But it can actually do more than just that, because if you have this hot expanding gas in this outflow, it can also interact with surrounding gas in the intergalactic medium. And so this gives you an additional halo scale preventative feedback that we include here. And we assume that this preventative feedback term on the halo scale is related to this ratio of the outflowing energy to the inflowing cosmological accretion. So that's the model. So we can now see how this works for an individual halo. So this is tracking these flow rates of energy and mass for a low mass galaxy. So this is 10 to the 11 solar masses for an assumed choice of each of the loading factors. So this is, and keep in mind, this is for mass loading of unity, so I think fairly low. And so first we can look at the flows of energy across time. And what we find is that after some early period of non-equilibrium mechanics, you quickly arrive at this sort of steady state of the energies where the halo scale outflows that are in that thermal expansion tend to balance out with the energy input from the supernova winds. And it's a product of this tight regulation that you also get this very slow fall off in the cooling efficiency as well, because the gas is in this thermally expanded state. And we can also look at what happens in the mass flows, and you achieve a similar regulation on the halo scale inflow and outflows. And this sort of works to keep the CGM mass roughly consistent over time, and limiting the amount of cooling that results into your galaxy. And so if we're trying to discriminate between different models of CGM and of feedback, it's not only important to look at the flows of mass between the reservoirs, but also these flows of energy. I think there's a lot of information that can be encoded by including this in our diagnostics of thinking about these systems. But of course, so this is just for a single halo. We can also do the comparison over a range of halo masses and compare to established relations like the stellar mass-halo mass relation. And so there are a few exciting things here, but I think the one that's most remarkably is, so if you keep for an assumed set for each of the loading factors, but you just vary one at a time, so if it's just varying the mass loading versus just varying the energy loading, you find that your resulting stellar mass is remarkably sensitive to what you assume for the eta E of the wind, the energy escaping in these outflows, but pretty insensitive to what you assume for the mass loading. And initially this may seem very counterintuitive that the resulting stellar mass would be very insensitive to the mass carried in these outflows. But this can actually tell us something quite profound about the interaction between these supernova winds and the CGM. Hello. That when the winds are able to efficiently deliver their energy to the CGM, that you're able to result in this thermal expansion that's able to limit the cooling efficiency, like we mentioned earlier. But also, if you mass load the winds, you lower the specific energy of the winds, which results in actually an increase in the cooling efficiency of the CGM, because not only are you delivering energy, but you're also delivering more mass. And so any mass you're delivering to the CGM quickly falls back onto you, resulting in very little change to your stellar mass. And so the last thing I'll show, just we're running out of time, is that what if you actually want to try to fit to the Brucy stellar mass relation? What is the best optimal choice of A to E that gets you that? And so what we find, once we actually try to fit to the Brucy relation, that A to E it should be a declining function of halo mass, suggesting that A to E should be larger in these low mass systems, but then gradually get smaller once you get to Milky Way scale. And which has a corresponding effect on the preventive feedback parameter, and also achieve the stellar masses in agreement with the scalings. And so with that, I'll just leave you with, I think, what is the biggest takeaway point, which is that thinking about the energy in these winds may offer a different approach of thinking about how feedback could be working on these large scales, and that I would advertise talks later from Viraj Pandya and Greg Bryan, which are expand on this idea both in simulated models and in simulations. And also leave you with this really beautiful summary slide from an upcoming paper from Mark Voigt, which goes in a bit more detail about why this is actually happening, why energy loading becomes more important when winds are able to efficiently couple to the CGM, and what happens when they don't, and the perils of what happens if you have mass loadings which are too high, both leading to problems if your feedback is uncoupled and coupled. And so I'm happy to talk about any of that or this talk. Thank you for your time.
Questions for Chris? There's one in the back first.
Hi, thank you for a really nice talk. I was curious, is it possible to pull out of your model what the mass and energy loading factor look like as a function of halo radius? Specifically, I'm kind of interested in, this is you have a single boundary here, and it looks like from your model you could kind of differentiate where material is being excavated and deposited, as well as where energy is being deposited, and see how those things differ as you kind of transition into the CGM. Is that something that you can pull out of this?
Wait, you're talking about like if thinking about like A to E and A to M as functions of radius?
Correct. Yeah, like spatially resolved mass loading factor profile.
That'd be exciting. Not as models like these, because with these sort of simple like bathtub models, you have to they're basically just like one reservoir that has very a few coupled descriptive properties to it. So not with something like this, but there are some exciting ideas of thinking not only about the thermal energy in these winds, but also their kinetic energy, which can also tell you something about how high these winds are actually able to reach in the halo. And we'll hear a bit more about that later.
Very nice. Thank you.
Let's do one more short question. And I want everyone who's giving a flash talk come line up here. Do you want to change slides? Yes, go ahead.
So thanks. This was a really nice talk that's changing my intuition a bit about low mass systems. I was interested in the cooling rate of the CGM, and so this is going to depend on not just metallicity, right, but also, of course, temperature and density. And so I wonder if you could say a bit about what sort of assumptions go into that as the hot winds expand and decrease in density and temperature.
Yeah, so like we have a model that describes the cooling, so the cooling would be a function of the density of the gas, the temperature, and the metallicity. So all of those are inputs that go into that cooling eCool that you found there. And so and also a cool thing about this model is that like we calculate the temperature itself consistently, so we don't just rely on the virial temperature. And so because of that raised temperature, we find that it's actually very inefficient. And even if you have a metal-rich halo, it's nothing compared to that increase in temperature and lower density you're getting from the expansion. Thanks. Great.
Let's thank Chris again. Chris, I need my mic back. I need my mic back.
Sorry.
I'm taking it home. Okay, so we have a round of flash talk before coffee. Thank you. Then you can probably just use the podium mic, right? Go for it. Yes, yes. All right, take it away. You got 2 minutes each.
Hello, I'm Cody Carr, and today I'm presenting on two of my projects involved with testing mass outflow rate estimators against simulations and then applying them to real data. My poster over there, number 49, today focuses on the ability of SALT, which is a forward model of galactic outflows to spectral line predictions, ability to measure the properties of outflows in the Fire 2 simulations. So here I'm showing some tests, our ability to measure the outflow rate versus time, and then as a radially dependent quantity. So there on the left, those black points represent the outflow rates of fire, and the corresponding inflow rates are in red, and note that they're out of phase. And then the blue points represent the estimates by SALT, and we see that when the outflow rate dominates the net flow rate, SALT does a good job, but then a large bias appears when the inflow rate starts to dominate. Fortunately, we can distinguish these two different phases in observations. When the outflow rate dominates, you get the nice blue shifted absorption we all know to identify outflows. And then in the opposite scenario, you get what we usually associate with ISM absorption. And then on the right, we find that we can do a good job of measuring the gradients in various radial properties. Although if the fire simulations deviate substantially from the analytical assumptions of our model, we can get a bias. And then I've used these models on the Class E objects, which we've heard mentioned in various talks so far. Here are a few of the highlights. So on the left, we found a positive correlation with star formation rate and the mass outflow rate. And then in the middle, we look at the momentum outflow rate and the energy outflow rate versus the predicted values from supernova. And we found that most of the momentum is deposited into the hydrogen, but most of the energy is not, and we're able to constrain the supernova energy efficiency to be about 0.1 to 0.001. Again, that's into hydrogen. So if you have any questions or like to see more of the results, please see my poster. Thank you.
Thanks. Sayak?
Hello, I'm Shayok. I'm a PhD student at IUCAA, India. So in this work, what we have tried to do is probe the distribution of neutral hydrogen in the circumgalactic medium traced by Lyman alpha, and the metal in the warm hot phase traced by O6 with our own MuseCube survey alongside a compilation of almost 5,000 quasar galaxy pairs from the literature. So one of the interesting results that we find is that the neutral hydrogen distribution has two different sources. Below virial radii, it mostly comes from this one halo term coming from the host galaxy CGM, and outside the virial radii, it's mostly contributed by the large-scale clustering of Lyman alpha absorbers in the galaxies. We find significant enhancement in the Lyman alpha absorption for the star-forming galaxies as compared to the passive galaxies inside the virial radii, and it's consistent with both stacked measurements and individual void profile fitted column density measurements. And we also see, as a function of halo mass, the Lyman alpha absorption profile shows a similar trend as of the star formation efficiency. Both of these quantity peaks at a certain halo mass and then it decreases onwards, although the peaks takes place at different halo mass regime. In terms of metal distribution, similar to what Sean presented last day, we also find a lot of O6 around low mass galaxies. And interestingly, these O6 column density for these low mass galaxies show a strong correlation with the host galaxy star formation rate. So probably indicating that these O6 are entrained by the star formation outflows for these galaxies. So that's about it. For more details, please visit my poster. Thank you.
Next we have Julianne Goddard.
Hi, I'm Julianne Goddard. I'm a PhD student from the University of Kentucky. I work with Dr. Isaac Schlossman and Dr. Emilio Romano-Diaz on this project involving the effects of AGN jet feedback on Seyfert galaxies. In the work I'm presenting here, we've run 4 high-resolution zoom-in cosmological simulations on the same galaxy. where we vary only one parameter. So we have one fiducial model where we don't see a supermassive black hole at all. And then we have 3 AGN models where we vary only a parameter associated with the accretion efficiency. So I have these 4 galaxies at z equals 0, the face-on projection. And I'm going to skip over all of the details and move on to give you just a tiny taste of the results. In these frames at the bottom, we have the gas evolution on galaxy scale in the small inset, colored by gas density. And then on the large, you have 2 megaparsec by 2 megaparsec frames for these 4 models showing gas colored by gas temperature. So on the far side, you can see the formation and expansion of these multiple generations of jet cocoons, which expand out far beyond the CGM into the IGM, affecting both gas recycling and pristine accretion from the cosmological filaments. When we look at star formation, we see that the overall effect of introducing the AGN is to reduce star formation, and that we get, a lower stellar mass as we increase accretion efficiency. We also see that star formation is pushed out to larger radii as we increase this efficiency factor.